Okay, so thanks everyone. This is May 30th's presentation for Kitchener-Waterloo Video Tech Meetup. Today we have Pavel Novotny, who's the Chief Video Codec Architect at AMD. As I said previously, I had the pleasure of working with Pavel for a number of years, and today he's going to be presenting the pros and cons of CPU, FPGA, GPU, and ASIC-based encoding platforms. So feel free to kind of take over, start the presentation then, I guess, whenever you're ready, Pavel.
Great, thanks, Chris, for the introduction. So let me share my screen. Okay, and I've got my presentation here. Hopefully, you can see it. So as Chris announced, I'm the Chief Video Codec Architect at AMD. I came to AMD through Xilinx, before that NG Codec, and before that all the long story of companies we were just chatting about with Chris. So today I'll be covering the pros and cons of the CPU, FPGAs, GPU, and ASIC encoding platforms. A little bit of background on me. I'm kind of pushing 24 years of experience in video encoding business, and over the years working with many talented people like Chris and Anthony here and many others, I had the opportunity to put my hands on all the different platforms I'm kind of aware of, which are the CPU, GPU, FPGAs, as well as the ASICs. And working on a number of different applications like encode, decode, transcode, all kinds of pre-processing, QA, and many other related things. And with that, kind of gain a little bit of perspective on each platform. And I did notice that over the years, the different platforms became kind of dominant for a certain amount of time, doing really well, only to be replaced by some other platform a few years later. And this cycle kind of tends to repeat. Things new things appear to be appearing and then disappearing, just to be and being replaced. And so today kind of we'll go over those things. And over my career, I started in Bigstream. Back then we were doing ASIC MPEG-2 encode, although back then we were really just consumer or users of existing ASICs. But then after that, we started to develop FPGA for H.264, then ASIC H.264, then eventually CPUs came along implementing H.264. Then we've got into FPGAs implementing HEVC and AV1. GPUs came along implementing H.264, HEVC, and then most recently we built AV1 ASIC. And so today I'll try to cover the different benefits and disadvantages of the different platforms, and try to kind of put all that into perspective. Well, let's start with the CPU or software encoding, and everything kind of starts with a software encoder running on a CPU, whether it's really intended as a software encoder, real-time or non-real-time encoder, or whether it's just some kind of model architecture or algorithm model to aim the development of FPGA, GPU, or ASIC implementation. The really kind of interesting event happened around 2015 or so, once the CPUs became fast enough to allow real-time 1080p 60 encoding, full HD basically in software. And there are a couple of interesting technologies which enabled that. One was the AVX acceleration, which added 256-bit instructions. And the other was many core cloud-based CPUs were becoming available by many cores, typically something like 1632, and also internet streaming together with the interaction of the cloud services became a thing. And so the internet was basically full of CPUs, and people very quickly discovered that running software encoders on those CPUs is a really good way of enabling the video streaming services. Around the time, I don't necessarily remember exactly the timeline, but FFmpeg and X264 became quite popular and effective in terms of coding efficiency, easy for people to use and deploy, and so together with the cloud services, that really enabled the internet streaming. In terms of the benefits of CPU-based encoding is that definitely a fast-to-market type of application, easy to deploy, right? Lots of people can program it. It's relatively easy. It becomes a lot harder once you really get to the final stretch of optimizing it for speed and whatnot. But there's in general lots of available talent. Lots of people can program in C, C++, and some high-level intrinsics and whatnot to really optimize the code. But in general, the barrier of entry is not that high with the CPU. It's also, as we know, software is easy to update, right? And also the CPUs can be time shared with other services. So maybe during the prime time in the evening, the CPUs get mostly allocated to be streaming video, and at night maybe they are doing some background encoding for Netflix. And speaking of Netflix, that's another benefit where for the CPUs where these offline encoding, it's a really good fit for the software encoders where the software can run pretty slow. You can spread the job over many CPUs and just let it run in the background, and that's kind of the model Netflix is using. The disadvantages of CPU-based encoding is that they tend to be pretty expensive, especially those many course cloud-based or server-based CPUs. They cost in thousands of dollars, right? And you really need those very beefy CPUs to be able to run like real-time video at 4K, and so you very quickly run into cost. Also, these CPUs take hundreds of watts per power, so that starts to add up. Also, there's a big difference between offline encoding and real time, where in the real time, especially the high resolutions, you really need to chop up the encoder into many threads, and you start running into VQ limitations because encoding processes prefer like a single-threaded serialized operation, and once you start breaking two threads, you typically have to start introducing some limitations into the design, which then have some VQ impact. So, and the more you push towards high resolutions, the more obvious it becomes, and that's why you typically have to like significantly throttle those encoders back towards the fast presets, and then the VQ subsequently suffers. And software encoding is because it's kind of at the mercy of the schedulers and whatnot. It's not really practical for ultra low latency applications. It's really hard to control the timing, and especially once you start getting into the millisecond scale, it's really hard to guarantee latency through the encoder. So those are kind of the benefits and disadvantages of the CPUs. Maybe I can pause here for a second in case anybody have any questions here before I move to the next slide.
Is there anything, maybe you're covering it in later slides, but like, are there different codecs that prefer different kind of platforms to encode on? So like, is a software solution or software encoding better for more newer codecs, I guess, because the support in the hardware isn't there for like not just AV1 is there's new hardware support for it, but would you have said before there was hardware support that one of the benefits is that you can encode in basically any codec in software, I guess?
Yeah, the CPU can run anything, right? We know that. Yeah. Question is how fast or how efficiently and how well that task can be performed. So if you look at legacy compression formats like MPEG to H.264. They are very lightweight for today's standards, and also the instruction set the CPUs provide are a reasonably good fit for those codecs. So you get really good acceleration. Once you move to the new codecs like AV1 and VVC, they are much more complex. They give you much more options, and if your aim is the best possible VQ, it just takes forever for the CPU to evaluate all the options and come up with the optimal decision. And also some of the maybe transforms or motion compensation, maybe some of those operations don't necessarily are great fit for the existing instruction set, and eventually the CPU people will catch up and beef it up. But there's a period of time where the new codecs are just taxing the existing CPUs beyond practicality.
That makes sense.
And again, it comes down to what your aim is, right? Let's say you want to implement VVC. If you want to do fully blown VVC, it will take insanely slow, but you can still implement a very, very lightweight subset of VVC, which will run just fine. But then at that point, you are maybe looking at quality of H.264 if you really cut corners, right? So it's always a trade-off, speed versus the CPU requirements.
Yep, that makes sense. Thank you.
Mm-hmm. So let's progress with the FPGA-based encoding. I spent a number of years developing FPGA-based encoders. So typically, when people say FPGA, are you guys familiar with FPGA, field programmable gate arrays?
Yep. Yes.
So typically, the first thing comes to mind is that FPGAs are for prototyping, right? You have some little design, you test it on FPGA before you bake it into ASIC. And that's still happening, extremely useful. The FPGAs are extremely useful in this case. But at some point, maybe 5 years back, maybe 6 by now, the FPGAs became large enough that you can fit entire like high quality encoder into the FPGA and basically run it at full speed. So that was kind of a breakthrough, similar to the CPUs, right? The CPUs became at some point fast enough to run modern codecs. FPGAs became large enough to fit the entire design, and so that's one way of implementing the encoder. Basically, take the entire hardware design and then fit it into the FPGA if you manage to. Another popular approach is where you take the software encoder and you offload some parts of it onto the FPGA, and typically the something like the estimation part, which typically can be easily separated out from the encoder, and there's lots of opportunities for parallelism, like testing all the different intra angles or the motion estimation, so you can try all the different motion vectors and sizes in parallel. You can offload those things into the FPGA, bring all that back into the CPU, and the CPU will basically run the normative part, the final mode decision, which kind of like this sterile nature of the CPU-based processing. That's something we've done a number of times as well. But it's kind of complicated solution, right? You have to worry about the FPGA, you have to worry about the software, you have to have software people, you have to have the FPGA people with hardware FPGA programming skills. And often what happens is that the FPGA is treated as a stepping stone, where you are working towards an ASIC, but you first prototype it on the FPGA, assuming the FPGA is large enough to accommodate it all. And then once you prototype it on the FPGA, then you bake it into the ASIC. And often the FPGAs are also used as emulators, where you have you've done your ASIC design. And before sending it to the fab, you basically run the full chip simulation on the FPGA, and that way it runs much slower than the eventual ASIC, but you get the full emulation of the real system, and that's typically a very good thing to do before you spend millions of dollars on the tape out and the fab. So in terms of the pros. the FPGAs allow higher density and subsequently lower cost compared to CPUs. Also because you typically build a hardware-based encoder, the quality is constant for any resolution, unlike like described before. Let's say once you get into 4K and you want to run it in real time on CPU, you have to scale down the presets to make it run in real time. FPGAs don't have that problem; it either runs or doesn't. Regardless of the resolution, so that's a good that's a nice plus. And also FPGAs being programmable, they can be reprogrammed. So similar to the CPUs, maybe during the prime hours, you do video streaming. At night, you might be doing ML training, right? So it's not like a single purpose device. And because you run hardware designed encoders on it, the timing is predictable. Subsequently, you can start thinking about ultra low latency applications. And one of the project I was involved in is we built this ultra low latency encoder. It was FPGA based, where it was really targeting virtual reality. So basically, instead of having the rendering engine right in the VR, you would basically render it on a PC, put the encoder into the PC, capture the output of the GPU, encode it, and stream it into the headset. And it was done on like macro block level, almost level the synchronization, and the end-to-end, like glass-to-glass latency was, I think, something like less than 5 milliseconds or something like that. So again, that's kind of showcasing the strength of hardware-based encoders, where you can have very fine control and predictable response in terms of timing. FPGAs are not perfect, so they are hard to program. You are kind of dealing with hardware design, and so subsequently you need specialized skills and tools. Skills are hard to find, and the tools are expensive. And also because you are dealing with hardware design, it takes quite a bit of time to get right. Not as bad as ASIC, and I'll dive into it later, but it's still considerably. It's going to take a considerable amount of time, and subsequently, the FPGAs typically have a somewhat short. We are talking about a couple of years, 2, 3, 4 years of a window of opportunity before the FPGA-based designs are replaced by either CPUs, because the CPUs got a lot faster, or people figure out better ways to optimize the code, or more practically, they get replaced by ASICs, where once you move the design into ASIC, the ASIC can do typically a much better job at much higher density and higher frequencies. All right, that's what I have on FPGA. Any questions? Chris, how are we doing with time?
Yeah, we're doing good for time. Hojat, you had a question?
Yes, yeah. Like, can you please elaborate on the quad VQ? So getting higher VQ and higher resolution for real-time encoding out of FPGA. Why is that?
How is that? So it could potentially be a very lengthy discussion. I'm trying to figure out how to describe it in a few sentences. So a couple of things to kind of give you hints. One is that the FPGA, because it's you will apply hardware design, typically you will build it with massive parallelism in there. So while the CPU, ignoring multi-core, while the CPU tends to sterilize everything, right? One instruction after another, the FPGA, you can, let's say, build and block, which is doing transform. So instead of burning through maybe 100 instructions to do, let's say, a larger transform, you build that block, and once you have that block, and it might might take just a few cycles for the block to get all the data through. And it's not just that, it's also depending how you design it, maybe it takes 10 cycles to get the data through the block. But if you design it well, it might be able to take a new set of data every cycle, right? So there will be latency, but the throughput might be massive. And also, once you build this block, you might replicate it many times. You're basically trying to maximize the usage of all the gates available to you. So those are kind of the main things. Once you build these blocks and you figure how to utilize them well, you can just push an insane amount of data through it.
Yeah, makes sense. Yeah, thank you.
Peter, you had a question?
I'm curious to know where FPGAs are used in industry. Like, are they used in hardware-based encoding for prototyping, in custom encoding systems and solutions?
Yes to all. So as I mentioned, when new codec becomes available, for instance, AV1 or VP9 before the CPUs have the opportunity to kind of catch up with having sufficient performance, and before the ASICs are available, that's typically a great opportunity for FPGAs to implement those new compression formats, which are quite demanding. So like early high VQ encoders, because when you are dealing with high VQ applications, typically the cost is associated with the transmission. So reducing the bandwidth needed is what reduces your operating costs. So that would be one application. Another is like the very low latency encoders, where really hard before you have ASIC, it's really hard to do it with CPU. So FPGA-based encoders will fit really nice there. Also, as I mentioned, like kind of early, lots of startups will start with developing FPGA-based encoding to enable new services, to demonstrate new designs, and over time they might eventually lead. Those IPs might lead into ASIC development. I've seen there's also a bunch of supporting applications utilizing FPGAs, some advanced pre-processing and VMAF optimizations and whatnot. FPGAs are really good fit for those offloading heavy processing from the CPUs, and yet those applications not being widespread enough to justify the very expensive development of ASICs.
So there are commercial encoders that have FPGA?
Yep.
Okay.
Yeah. VT1, I think, is one that's being used in AWS. That's AMD is responsible for.
That's correct, yeah.
So should I raise my hand just to follow? So a question. Can I go on?
Please.
Yeah, go ahead.
Yeah. So I think going back to the VQ video quality discussion, I think when you think about VQ for every encoder, there is basically VQ, but you have to also talk about density and latency. So when you have a statement like allow higher VQ at high resolutions, are you talking about similar density and similar latency as the FPGA? Because as you're aware, I mean, a lot of encoders today run on CPU, and they can provide a very compelling video quality out of those. Yeah, if you compare density and latency, maybe there are some drawbacks there, but essentially you can have a pretty good quality out of the CPU encode. Can you elaborate on that?
That's right. It's about compromises, right? We know CPUs can do anything. Question is at what speed and how many cores and how expensive CPUs you need to allow those. I know this is kind of a generic statement about the higher densities and lower cost, but it's at the end you really have to kind of do a detailed cost analysis. What's the price of the CPU, and not just that, but also how many channels you fit there. What is the price of the bandwidth for the bit streams you are sending out, right? So operating costs, and you do the calculation for the CPUs, and then you do the calculations for the FPGA-based encoders. And obviously, there's a price to the FPGA. The larger the FPGA, the more expensive it is. But then also large FPGA allows you to have a more sophisticated design, which will have higher VQ, producing a lower bit rate, and less bits cost less money to transmit. So, it's kind of beyond the scope of this presentation, but once you put it all together, there are some interesting niches where the FPGAs become quite attractive compared to CPUs.
Thank you.
All right, let's move to GPU encoding. So there are kind of two ways how to implement encoding using GPUs. One is where you use the GPU cores to offload some of the processing, kind of similar to what I was talking about previously, using FPGAs instead of dealing with FPGAs. You offload it to CUDA cores. It's kind of convenience because GPUs are much more easily available, typically cheaper as well, but also a lot more people know how to program CUDA compared to programming FPGA, and in this case, you would be offloading some parts of the encoder to the GPU. And I believe there are some deployments, but I don't remember hearing about any of those recently. So I think that part kind of died down. Just kind of wasn't worth the trouble by going to the GPU, running it there, bringing it back, because you have to also move lots of data back and forth to enable this. And by the time it's kind of a wash in terms of how much the GPU is helping, because the GPU cannot do everything. You still have to do lots of the final normative processing on the CPU. So kind of building a more complicated solution for not much benefit. The other approach is where pretty much every modern GPU has a dedicated hardware encoder present somewhere on the die, and the purpose of that, or the reason for the existence of it, is to allow things like screen recording and remote gaming, where you can log in remotely into your PC, and basically the PC runs the game, but you are using your phone or some other mobile device as a remote display, basically. And so the nice thing about this setup is that typically the codecs inside the GPUs provide very high density. They can do multiple 4K P60 streams. They also support very high maximum resolution. Some GPUs can do 8K, and the built-in codecs can support that. Similarly, when it comes to high frame rates, and typically run at very low power, talking about a few watts. And typically, these codecs are designed for those applications, and that means low latency or ultra low latency applications like the remote gaming is the primary target there. And the really nice thing is that they are readily available in most, if not all, GPUs you can buy today. So the adoption is very easy. The disadvantages are that these codecs, they do compete for silicon power and bandwidth with the GPU cores. Like, if you go to buy GPU, who is wondering about what are the encoding capabilities of the GPU? Nobody, right? We all care about how many CUDA cores there are, and they take silicon, and that's where most of the silicon needs to go towards. And subsequently, if you, as a Codec Architect targeting the GPU, you will be operating under lots of constraints. So subsequently, the quality will be reduced, because the codecs typically implement a small subset of the overall tool set, especially when they are just targeting the low latency and ultra low latency applications. Some of them might not be supporting B frames, for instance. So if you are trying to use the GPU as a pure encoding solution, there's going to be a lot of waste, right? Because the entire GPU is unused, and you are just using this tiny corner of the silicon implementing the hardware encoders. So kind of wasteful in some regard. Also, these GPUs tend to be beefy as opposed to a nice slick card. So the system level design, or rather system level densities, is typically not as great. And also, these codecs typically are developed as a kind of a checkbox item as opposed to a primary focus. The primary focus is the GPU cores, right? So the encoders are there just to enable these secondary convenient applications. So subsequently, they are not targeting high VQ applications, not dedicated focus teams. So yeah, so that's what's kind of the state when it comes to GPU encoding.
Aaron?
Yeah, so I guess what you're saying is that the GPUs are kind of ASICs in disguise. That it's an ASIC with a GPU glued on top of it.
Well, I cannot get into the details, but yeah, there's most of the silicon is going to be GPUs, and somewhere there is the GPU cores, and somewhere there is going to be the little ASIC encoder.
As I understand it, GPUs are highly parallel floating point systems.
Mm-hmm.
They aren't suitable for use as video encoders?
Well, that was kind of the first point I was discussing here, right? You really have to dive into the details of video encoding and identify what's a good fit, what is not a good fit. What are the instruction sets of the GPU cores, and what are kind of the data requirements, how to move the data between the cores and between the host. And subsequently, so you can do things, but once you go through all that effort, you realize that you are building something pretty complex, which just might not be worth the trouble unless for some special niche applications. Where the GPU cores are useful is by doing additional processing on top of the encoding. So the encoders can be kind of treated as the final stage, but before that, you might run some noise filtering, you might run some content enhancing, composition and whatnot, background blurring. And once you do all that on the GPU cores, and there are many readily available applications to do that, once you establish that flow going through the GPU cores, you stream all that into the encoder, the hardware encoder, which will do the final encoding. That's typically how the GPUs are used.
Thanks.
All right, let's talk about ASICs. I spent, I think, most of my years working on ASIC, and definitely the most challenging and exciting projects. So ASIC is basically a custom-built chip which is dedicated, well, in this case, dedicated to video encoding and transcoding. And typically, when you build it, you aim high because development is very, very expensive. So these chips these days are very capable. They can support multiple 4K P60 streams in a small package with very small low power requirements. And there's typically a lot more going on in the ASIC as opposed to just, let's say, encode. There's pretty much every time. There's decode, some kind of scaling, filtering, might be composition engines, multi-format encoding, right? These ASICs typically support, like these days, it's pretty common to have H.264, HEVC, and AV1 support all in there. So the idea is that you bring the bit streams in, you do all the decode processing, rescaling, reshaping, and whatnot, all on the ASIC, including the final encoding, and just the final bit stream is going out with very little, interactions from the host. Typically, most well-designed ASICs don't need to send the uncompressed video back to the host for some processing before it's sent back into the chip for the final encoding. So it all stays within the package, which makes it much more efficient from system perspective, but also power and latency and all that. In terms of the pros, definitely the best solution in terms of the density, because the silicon and everything around it is 100% committed towards the video encoding or processing tasks. Subsequently, low power, low cost, and small form factor. Being a hardware designed, typically it comes with deterministic timing and then performance, as you might know, with CPUs. Even if you, let's say, encode something on your PC and you bring up the task manager, the CPU utilization level going up and down all the time a little bit, sometimes more, sometimes less, right? So that's variable load, whereas the ASICs tend to run in a constant load. So whether the content is easy or hard, the timing will be typically very, very stable, and subsequently with that you can be targeting lowest latency applications with predictable density. As I described, a typical well-designed ASIC will keep all the processing on the chip, so subsequently minimal host CPU loading, and similar to what I described with the FPGAs, typically the design is agnostic of the resolution, so the quality or compression efficiency will be constant regarding the resolution. And at some point, as you are increasing the FPS or the resolution or the number of channels, eventually the ASIC runs out of performance and it will not run any faster when it's fully maxed out. But the response and the quality and efficiency of the encoding is going to be consistent. Disadvantages, it's expensive and time consuming to develop the ASIC-based solutions, and similarly the upgrade cycles are multi-year, right? It's just also often well aligned with how these things are deployed. Customers typically cannot take a new version of the ASIC and the board every few months, even if it's available, because they spend lots of effort to integrate these devices into their flow and getting fully confident and make it everything reliable. So once they have it working, they want to kind of keep utilizing it for a number of years before they have to upgrade. But yeah, it's a pretty expensive process. It's very narrow niche, requires very specialized knowledge and expertise and many millions of dollars upfront before you start making money of those efforts. There's very little room for any errors, as silicon cannot be fixed afterwards, unlike the FPGAs, which can be reprogrammed, or even easier CPUs, right? If you have a fix, you just debug it, recompile, and upload the new version. Doesn't take much effort, but you don't want to have any bugs in the silicon. Because you typically cannot fix it easily. Sometimes you get lucky, and typically the ASICs have CPUs inside, and you can work around some issues. But other than that, it typically becomes very pricey if you have to like respin the chip and whatnot. And because of the upfront cost associated with ASIC development, it needs to be targeting a very high volume applications like hyperscalers, companies like Google and Facebook and others who have massive amount of data, video, which needs to be processed. And the one caveat with all hardware-based encoders is that to be able to produce designs with predictable timing, there's typically and running at desired speeds, there's typically some kind of hardware pipeline under the hood, and that might or may not introduce some limitations to the VQ, kind of like what I talked about earlier with the CPUs, where you have to break it up into many threads, and that starts introducing limitations. These ASIC-based designs or hardware-based design might have some limitations, but the most recent designs coming out are getting really close to like the best CPU offerings in terms of the VQ, yet running at much higher density and much lower power and cost.
Pavel, is there something that prevents us from going higher than 4K 60, like for 8K? Is it just that there's
No.
ASICs don't really target it, or is there a specific reason why you wouldn't have like an 8K ASIC encoder?
No, it's I kind of randomly picked that number because it looks big enough, right? You cannot impress with HD these days, and at the same time, 8K is not really mainstream, right? There's few services offering 8K, but not too many, just because of the cost. Just you cannot find enough people yet to pay for the extra resolution. If you think about it, 8K 60 takes the basically the equivalent of four 4K P60 streams, right? Just in terms of the processing power, but also the bandwidth, right? The bandwidth going to the client is much higher and it's more costly. So how many people are willing to pay for it until the codecs become so efficient and so cheap that you just won't think about it. So it's more of the practical cost associated with that. But even today's chips, they can do multiple 4K P60, and some chips are capable of pairing the devices together and be able to do 8K. That's not really an issue anymore. It's just the cost of deploying 8K services. That's really where the it's kind of the current showstopper at this moment.
Yep, that makes sense. Harald? You're a little quiet. Maybe if you type your question into the chat, it's a little. I don't know, Pavel. I can't hear him.
No, I cannot hear either. Maybe try switching to a different microphone.
Yeah, or you can type your question in the chat and I can ask it.
I cannot hear it.
No. Why you hesitate to call GPU encoders ASIC encoders?
Pardon me?
Harold's question is why do you hesitate to call GPU encoders ASIC encoders?
I don't hesitate. It just they come as part of a GPU, so I was kind of trying to keep it separate from that perspective. But the stress here is that when I call ASIC encoders, they are like dedicated ASICs to just encoding or mostly encoding, whereas GPU is really a graphical card, right, or a bunch of CUDA engines, which also happen to be happen to have a hardware encoder somewhere there.
Yep, thanks.
All right.
Can I ask? Yes, yeah. Just before moving on, Pavel. So as you mentioned, you have a lot of experience designing an ASIC encoders, and you've worked with many platforms, GPU, CPU, ASICs. The very first question that I have is how important VQ is to you guys when you design an ASIC encoder, let's say, or you put an encoder into ASIC. This is one, and the second, if it matters to you, what sort of testing you do to make sure that like a VQ is maintained?
So for the first question, there are many different ways to answer that, but one reason I'm trying to be a bit funny is that, like, if you are shopping for a car and you come to a GM dealership, the first thing you will see a Corvette, right? And you will stop and look at it, and then you might end up buying an SUV. So a little bit of that, where the very high VQ is really good for advertising. And then in practice, people are, because it all costs money, right? If you can fit 2 channels as opposed to 1 high VQ channel through the chip, you are kind of cutting your costs to half. So the balancing those aspects is important. And also there are different applications. Some applications again, it comes to the cost, and some applications appreciate more the bitrate savings, which come from the very high VQ encoding quality. Other applications are not as sensitive to the bandwidth savings, and instead they are more sensitive to the cost of the solution. And if you can fit twice as many channels through the same hardware, you cut your cost to half. So it really depends. Ideally, a good ASIC design is flexible in the form of that you can runtime switch it into high VQ mode, reducing density. But for those applications which require high density and are more cost sensitive in that regard, you can change the setup of the ASIC to be targeting high density, lower VQ applications. Some ASICs, whether it's ASICs or GPUs and whatnot, do allow you to do those sort of things. Similar to the CPU, right? You have those presets, fast, medium, slow, and whatnot. Some ASICs provide a similar capability.
And what sort of testing you do? Like, I think you forgot this part of my question. So what sort of testing you do to make sure that the VQ is maintained? Or do you, like, when you say that this platform gives you higher VQ and the other one lower VQ, like instead of like how do you objectify this? Like how do you objectively measure video quality? Or maybe you do subjective studies. How do you make sure that VQ is maintained?
Well, definitely all combinations of everything you mentioned, right? Objective as well as subjective. But it also comes down to the product definition, right? What are you targeting? Are you targeting more towards the high VQ applications, or are you targeting more of the cost-sensitive, high-density applications? So it comes from requirements, but then typically the next step after that is developing some kind of model which represents the final product, so you can demonstrate that you did achieve or hit the requirements as expected, and out of that you build the actual product, ASICs in this case. But yeah, it takes lots of testing, lots of verification, because as I mentioned a minute ago, you don't want to have any problems once the chip comes back. I hope I answered your question.
Yeah, thank you.
Benham, you had a question?
Yeah. Hi, Pavel. Right now, we
Hi.
are seeing the newer generation of encoders called marketed as ASIC. For example, the ones that are provided by NetInt, and they are comparable. The speed that they are providing and the power consumption that they are providing is comparable with the ASIC, pure ASIC. But we see that they receive updates. They receive new features in each update cycle. Does this mean that these kind of encoders are a hybrid kind of types? And if so, how do they have this software inside, which is fast enough to be working like an ASIC?
Well, I'm quite familiar with those offerings. I'm not sure how much I can really dive into the details of it though in this call. Maybe a generic question is or other answer is it comes down to the application you are trying to implement with the particular chip. In this case, you mentioned NetInt, and you have to look at the capabilities. And for instance, I mentioned that a well-designed ASIC might have all kinds of acceleration engines available on the die without any need for the video to go back to the host. So, the NetInts, I don't think they are known to be particularly feature-rich, and I believe in many situations you can use the built-in decoder to decode the video in the chip, which is very efficient, but then you have to transfer the data, the decoded video, which is a lots of data, over the PCI bus into the CPU for some processing. At that point, you likely need quite a beefy CPU to be able to handle all that traffic the ASIC is capable of generating. Then you transfer everything back into the ASIC for the final encoding. I cannot quite comment on kind of trying to make a generic comment without having an exact scenario, but it's likely something along those lines.
Thank you.
Yeah. All right, so just kind of trying to summarize everything. So the CPUs are often, as we've seen over the years, are often the first movers after the CPUs actually became fast enough to make it practical. And they are also really good fit for non-real-time applications where you just can take a long time to encode at the best possible VQ, but they tend to suffer from costs at scale. At the same time, FPGA can kind of bridge the period when kind of people get excited about all the services the CPUs enabled, but very quickly things start to scale beyond what's practical with the CPUs. But before people have a chance to spool up their ASIC teams to basically optimize hardware solutions for those opportunities. But then once that happens, ASIC is the long-term winner, especially when it's well designed. But as we discussed, it takes several years, and it needs a very large market to really justify all those costs and efforts. So kind of the moral of the story is that once you develop a solution, you don't want to be assuming that you will be able to keep offering that solution for forever. Something new might come along which will address that better than your existing solution, and the next technology might replace your offering. So even if you have something working really well, you want to be kind of looking towards the next trends and be ready. Otherwise, if you are not, somebody else will.
That was great. Thanks, Pavel. I really liked the summary. Do we have any other questions? I know we're butting up on the hour, so Peter? You're still muted.
Seems like there's a general belief in the industry that software-based encoders always produce better perceptual quality. I know you've come from that hardware world, so can you comment on that a little bit? That the best software encoders will always produce better perceptual quality than the best hardware encoders. So for, like, let's say a streaming service provider is most interested in quality and not as interested in cost, would the software-based approach always be the best option for them?
The answer is always it depends. It's about compromises, and with the CPU, you have the flexibility of always take longer to encode particular a piece of the video, right? Try more modes, try different angles and whatnot, and you can basically trade encoding time with quality. And if you are willing to take infinite amount of time, you will get the best possible quality. So you have that flexibility, and that's likely where the perception is coming from. Like, for instance, if you take something like X264, X265, and you run it in slow or very slow preset, it will take impractically long to encode, but it will give you better quality. On the other hand, if you take some ASIC, and ASICs are typically trying to target a certain market segment, they will make some compromises, and at that point, you are kind of to some degree stuck with that, right? And you don't have at least many ASICs. You kind of don't have the ability to just keep cranking up the VQ and be trading the encoding time and density as much as you can with the CPU. So subsequently, the ASICs typically have kind of stop, not kind of in the, if I use the X264 or FFmpeg terminology, they might not necessarily be targeting the slow and very slow presets. They might be typically stopping at medium and whatnot. Because that's where most of the volume, most of the money is, right? The applications where you really appreciate the quality, maybe Netflix, because you encode once and you typically distribute many times. So if you are encoding a movie once, you can take a week to encode a 2-hour movie, right? No problem. But then you want to encode it into as few bits as possible because you are sending it out many times, and so the cost of transmission becomes significant, not as much the cost of encoding. So whereas ASICs are targeting a live real-time encoding, and because of that, they are more typically interested in targeting the markets where you have to service high-density live encoding, where the cost of the service and the hardware associated included is more prevalent than the absolute VQ. But there's very little really preventing ASIC designs to be hitting very high VQ levels, as I kind of alluded. The latest designs are capable of getting very close to the CPUs, and with enough time and money, the ASICs will keep improving and getting where the software encoders can be as well.
Thanks.
So yep, we're up to the hour now. So without any other questions, I'd like to thank everyone for joining, and thank you again, Pavel. It's great to see you again, and hope we can do this in person in the future. So yeah, so with that being said, if you're in Southwestern Ontario, enjoy the warm weather. It's going to get really warm. Hope you stay cool. And otherwise, I think this will be the last one until the fall Kitchener-Waterloo Video Tech Meetup. And that being said, yeah, wish you all a great rest of your day.
Well, thanks for having me.
Yeah, thanks.
Take care. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thank you.